Hello, welcome to the inverse square law simplified. Just a pre-note. You've heard the horror stories of the inverse square law. Please let go of everything you've heard before this presentation so we can simplify it and start from the beginning. Light versus X-ray. The hardest part of learning the inverse square law is not being able to see what you're talking about. X-ray beams and light are very similar, and you can see light beams with your own two eyes, so let's start there. Over here on the left, you can see the X-ray tube, collimator box, and your beam that's going down to your patient. You can see as it gets closer and closer and closer to your patient, the less energy that those rays are having because they are diverging and losing energy. Now your X-ray beam goes through your patient, through your table, and then in your image receptor here. So these little dots here are where your beam has gone through your patient and hit your image receptor. Now just as these rays here are diverging and losing energy, the rays from a light bulb do the same thing. So the closer that you are to the light, the more focused the intensity of the beam is. So the rays of light travel just like X-rays. They diverge or spread out over the area as they leave the source. Therefore, the farther away from the source an object is, the more widespread the coverage is. However, as the rays of both X-ray and light travel farther away from the source, they also lose energy and become less powerful. So as you can see here in the picture on the left, the light source is here. In this first image of the man standing in the photo, you can see that the light is focused on a small area in the center of his face. The farther away he is, the more light is focused on his face until you can actually see his whole head. But if you look up at this very first image, you can barely even tell that he has a head. So in the last one, you can see his ear and everything, whereas if he is closer, the intensity is so focused that you can't see anything past his face. So why do radiographers need to understand the inverse square law? The intensity is extremely important when a radiographer is deciding what source to image receptor distance, or SID, to use, and what technical factors to select. The patient's size and body part of interest are very important in the decision as well. Tissue densities of the body also make a big difference. But in the end, it's important that the radiographer selects the best intensity for the X-ray beam to travel through the patient and give a diagnostic quality radiograph. Okay, here's a real life example. On the left, there's a 40-inch SID used on an upright bucky. I taped a remote control and I took two pictures. And like I said again, on the left is the 40-inch SID. On the right, I used a 72-inch SID. So right off the bat, you can tell that there are different intensities on each of these images. So which do you think would be more intense? Of course, it's going to be the one that was closer. So in the image where I took the radiograph at 40-inch SID, you can see the batteries and other metal components really well, but you can barely even tell that there's plastic around the edges. So there's no detail at all in the plastic, and you can barely even tell that there's detail in the batteries. So when we move back to 72-inch SID, the metal components show up really well. You can even see some things on there that you didn't know existed if you were looking at the 40-inch SID image. So all the plastic parts show at 72 inches. Everything looks like it's in great detail. You can see by these two images that you can distinguish what the image is at a 72-inch SID Whereas if you were looking at the image from 40-inch SID, there's a possibility that you wouldn't even know what it was. So, what's your point, Whitney? Well, since the X-rays from the shorter SID are stronger when they hit the image receptor, they do have more penetrating power. The image from the shorter SID is going to be much darker and harder to understand. The image with the longer SID has X-rays that are not strong enough to penetrate all of the plastic material, so they give more detail and you can see inside the remote control what's actually there, not just a black space. Now, both images were shot with the exact same technical factors. The only change was distance. So distance is pretty important, right? The rest of the story. You may think that it's important to have the most intensity or penetration power out of your X-ray beam, but as you can tell on the previous slides, it's best to have the right amount of intensity so that the tissues are penetrated perfectly, yet also not as attenuated as the image for the 40-inch SID, because you do want it to have better diagnostic quality. So how do you adjust the intensity of that image? Do we want to change our technical factors? Well, maybe, but in this case, we're going to use the inverse square law. A quick look at the inverse square law formula. I want you to keep in mind that I is intensity and D is distance. So just like with any other formula, we're going to start out on the left. Our I intensity number 1 over intensity number 2 equals the distance squared from distance number 2 over the distance squared from distance number 1. What? Yeah, I know. This is so exhausting and it's a lot and there are so many numbers and symbols and what is going on? Okay, let's break it down. The inverse square law is simple. It's as simple as mass or milliamperes per second and distance. Now I know you're thinking I'm crazy, but let's get a little deeper into it. So the old mass or milliamperes per second over the new mass equals the new distance squared by the old distance squared. Does that start to make a little more sense? Okay, let's get an example of what we're talking about here. I'm going to be using a question and an answer that came from the Bushong textbook, and it goes like this. Mobile radiography is conducted at 100 centimeters SID and results in an exposure of 0.13 milligray at the image receptor. If 91 centimeters is the maximum SID that can be obtained for a particular examination, what will be the image receptor exposure? So since we know that we're looking for an exposure, we know that we're going to be looking for an intensity. So that's going to be our intensity 2. Our intensity 1 is a 0.13 milligray. So our equation will start out as 0.13 milligray divided by intensity 2 equals 91 centimeters squared divided by 100 centimeters squared. So intensity 2 equals 0.13 milligray times 100 centimeters squared divided by 91 centimeters squared. Then intensity 2 equals 0.13 milligray times 1.1 squared. And then 0.13 milligray times 1.1 equals 0.14 milligray. So our intensity 2 equals 0.14 milligray. Okay, now on to the complicated part. This equation can show us how to change mass and keep the same distance to get a similar exposure, change the distance and keep the mass the same, shows us how a radiation source's intensity decreases the farther it's away from an object because the remaining energy is spread out over a bigger area. When being exposed to a radiation source, if a radiographer steps by double the distance away from the source, it will quarter the dose to the radiographer. So it helps us protect ourselves from scattered radiation. Let me go over that one more time. When being exposed to a radiation source, if a radiographer steps back by double the distance from the source, it will quarter the dose to the radiographer. Let's add that in there so that we don't forget. Back. So if a radiographer steps back by double the distance from the source, it will quarter the dose to the radiographer. Do you realize how much that means when you're being exposed every day to radiation? That's a huge deal. So let's talk about the world of the inverse square law according to Bushong. The inverse square law is when light is emitted from a source such as a sun or a light bulb, the intensity decreases rapidly with the distance from the source. X-rays exhibit precisely the same property. Figure 315 shows that as a book is moved farther from a light source, the intensity of the light falls. This decrease in intensity is inversely proportional to the square of the distance of the object from the source. Mathematically, this is called the inverse square law, and it's expressed in the equation that we've already gone over. So we already understand how the inverse square law works. But when I read these words, it's really hard to understand. So even at the top right here, it's easier to understand what Bushong is saying by not reading the part in yellow. So we're wanting to simplify this, so let's go back and read that again. When the light is emitted from a source, such as the sun or a light bulb, the intensity decreases rapidly with the distance from the source. That is basically the only thing that we need to know about the inverse square law, other than the equation and how it works. So let's go right here. We're going to circle this part because this is what we want to know. So once again, when light is emitted from a source such as the sun or light bulb, the intensity decreases rapidly with the distance from the source. So the farther you get away from your source of radiation, which is your X-ray tube, the more the intensity decreases. Now, since that's inversely proportional, the square of the distance of the object from the source is going to be your difference of intensity. Let's take a look at our inverse square law formula. I want you to keep in mind that I is intensity and D is distance. So on the left, we're going to start out with intensity 1 over intensity 2 is equal to the square of density 2 over the square of density 1. So I want you to keep in mind here that On the intensity side, we're starting out with intensity 1. On the density side, we're starting out with density 2. That's what makes it inversely proportional. A couple of really important notes that I wanted to go over with you are that the inversely proportional term is very important. You're going to hear that in tests, and it may even be on your registry. It's very important to know the difference in the inversely proportional term and the proportional term that's used with the square law. Of course, the inversely proportional terms are going to be used with the inverse square law. And something that says either directly proportional or just plain proportional is going to go with the square law. I also wanted to let you know that the inverse square law, as we know it today, was discovered by Isaac Newton when he was studying gravitation. It's been adapted for other things like being able to express light and being able to express radiation. Because the two are so similar, they're used together a lot in radiation demonstrations. It's a whole lot easier to look at a light source and see this inversely proportional decrease of intensity because we can actually see it with our own two eyes. We can't see radiation, so it makes it so much harder for us to understand. I hope you've enjoyed my presentation today. I do have a few works cited listed here. Of course, I used the Bushong textbook, the 11th edition, and I got a couple of images from one of the websites that's listed there. If you have any questions about any of my resources or anything, just let me know. I hope you've enjoyed. Have a good day. Bye-bye.